Hey, this is Jen. I'm making this recording to explain the microscopic origin of the ideal gas law. So before we get started, there are a couple things you should know about physics. First, that physics is what is called a reductionist science. That means that physics would like to be able to explain a wide range of phenomena from a few basic principles. Second, you should know that physics is always based on evidence, like pretty much every science. So there are times that we'll have empirical laws. These are ones that are discovered purely from evidence. The ideal gas law is one of these kinds of laws. And more than anything, we'd like to be able to explain or predict these empirical laws from theory. So the best kind of work in physics is when you can take some theory and explain empirical laws with it. And that is pretty much what we mean by reductionist, a few basic principles explaining a wide variety of phenomena. Before we really dig into how we can derive the empirical ideal gas law from basic principles, there are three key physics ideas that you need to remember. The first of these is momentum. Momentum is represented with the symbol P. It has a vector hat on top because it's a vector, it has direction, and momentum is defined as the product of an object's mass and its velocity. So you may be wondering, why do we need this special quantity if we already have mass and velocity? Well, it's because the combination of mass and velocity is more interesting. First of all, if something is going to run into you going 10 miles an hour, it matters a lot to your health and safety whether that object has a mass of 1,000 kilograms going 10 miles an hour like a giant train, or whether it has a mass of like a gram going 10 miles an hour. Those are very different experiences for you personally. The second reason is that momentum is conserved. It's a conserved quantity, and physicists are very interested in conserved quantities. So that's the first one. The second one you need to remember is Newton's second law. And we can rewrite Newton's second law. Remember, it's F equals ma. Net force acting on an object equals that object's mass times that object's acceleration. Acceleration is defined as change in velocity over change in time. And now notice we've got an m and a v here. And as long as the mass isn't changing, we can stick that mass inside the delta by distributing it. And so what we end up with is the change in momentum over the change in time. Now this change in momentum here, this, again, I said momentum is important. This quantity, change in momentum, has a special name in physics. It's called impulse. So the change in momentum of an object has this name, and you will see this frequently when we talk about collisions, the impulse that happens to an object during a collision with something. The third idea that we need to use in order to do this derivation is the idea that pressure has been defined as force for a given area. So combining these three ideas together, we are going to be able to show that the ideal gas law actually comes from a few small basic physics principles. Okay, so let's consider one atom of ideal gas in a box, and let's think about what this one atom might be doing. So this atom has some velocity, and this atom is moving around in the box. It's going to move in a straight line until the instant it collides with something, probably the wall of the box, and then it's going to recoil the other way. Okay, so we're going to make a few assumptions about collisions with the wall. We're going to assume first that in the collision the velocity reflects, so that the final velocity is equal to negative of the initial velocity, that it just flips directions. And so what that means is that the change in velocity of this particle is final velocity minus initial velocity, but the initial velocity is the negative of the final velocity because it's reflecting. So that's going to be, and this is an F, so that's going to be 2VF. And I put the vector hats on here, but I've drawn this particle so it's moving back and forth in the x direction. So I'm going to put an x subscript here just to show that it's moving in the x direction. And finally, because its velocity isn't really changing except directions, we could even just get rid of this f. So we can just talk about how this is 2 times the velocity in the x direction is the change in velocity. So we're interested in knowing how much force or how much pressure a single one of these particles exerts on the wall. So we're saying that from one particle, that force is going to be Newton's second law, change in momentum over change in time, all divided by area. And change in momentum is change in velocity times mass over change in time all over area. So we do know a little bit about this change in velocity. It's going to be m 2vx. So I'm substituting this change in velocity here into our Newton's second law expression there. Now we can think about what this time means. So how often does this particle collide with this far wall of area A? Well, it's going to collide with that wall every time the particle travels it hits here, then it has to go here and back again. So the amount of time it takes is the time to cross the box twice. So we can figure out that time assuming that it has a constant speed. So time equals distance over speed, and the distance is going to be 2 times the length of the box divided by its speed, v sub x. So I'm going to take this and I'm going to plug this in to the denominator there. And therefore I'm going to have 2L divided by v sub x, and all of this is multiplied by the area of the box. Now we can do a little bit of cleaning up. So we've got a 2 in the denominator that cancels with a 2 in the numerator. We've got this v sub x in the denominator of the denominator, which means it flips up to the numerator. And we've got L times A, so length times area will be the volume of the box. Now again, let's just remember, this is the pressure from one particle of ideal gas. Now what can we do when we extend this to a whole box full of ideal gas? So now if we have the pressure from n particles, we're going to multiply that expression by n, and we're going to extend this to 3D. Right now we've sort of just been considering a particle that bounces back and forth, but really these particles are bouncing at angles in all different directions. If you watch one of the PhET simulations, you can see this. And so we sort of know that if we have an x component of velocity and a y component of velocity, the total velocity is going to be the Pythagorean theorem of the two components. We can say that in 3D too. So we know the average velocity of one of these gas particles squared is equal to its velocity in the x direction squared plus the y direction squared plus the z direction squared. And there's no reason for these speeds to be any different from each other. So if they're all about the same, why shouldn't they be? Then we can say this is equal to 3vx squared. And finally, we can replace the vx squared, the average, it's going to be the average speed here now with n particles. It's going to be 1/3 of the full velocity v squared. Okay, so I'm going to take this and I'm going to substitute this in up here. So our pressure from n particles of ideal gas is the number of particles n times 1/3 m v average squared all over v. The other thing I want to point out is that mv squared, this kind of looks like kinetic energy. Kinetic energy is 1/2 mv squared. So we can say the average kinetic energy of one of these gas particles is 1/2 m average velocity squared. And so if we put in to this thing a 2/2 like this, that's a factor of 1, I can take the one in the denominator and say, aha, this is the average kinetic energy of one particle. And so now I have n times 2/3 1/2 mv squared all over v. Now we finally have something that looks kind of like an ideal gas law. We have the pressure from n particles multiplied by the velocity equals 2/3 times n times this average kinetic energy of one particle. So finally, we are at the point where we can compare the empirically derived ideal gas law, PV equals nkt in physics form, against this PV looking thing that we just derived from basic principles, which is PV equals 2/3 average kinetic energy. And if we line these up, so we're going to compare, kind of like we do when we linearize, we're going to compare the parts that are the same. So the P and V are the same, and the N is the same. So what that means is that the Boltzmann constant, kBt, has to be the same thing as 2/3 times the average kinetic energy of a single gas particle. And this, remember, this is ideal gas because we're not considering interactions with other objects or anything like that. So that means that the average kinetic energy of an individual ideal gas particle is equal to 3/2 kBt, and the total internal energy of a gas, this thing that we've been calling U, is equal to the number of particles times the average kinetic energy of one particle, which is equal to 3/2 n kBt. So we've been using this equation. I haven't told you where it came from, but now you know where it comes from. Okay. So one last thing here. There's a pretty common AP thermodynamics question that appears in various ways and forms, and it has wording something like this: how can we correctly explain the changes in collisions between gas molecules and container walls that contribute to the change in pressure of the gas? So you should be able to answer this question in terms of the derivation we just did, and I'm going to show you how. So I just want to say one more thing. If you have a sample of ideal gas in a box and you increase the temperature by either heating or working on this thing, how exactly, from a microscopic perspective, does that change the pressure? Well, let's look at this version here, sort of an intermediate version. Doesn't quite look like the ideal gas law yet, but we can see really clearly that if you make the particles move faster, either by heating them or by pushing them with a piston, by doing work on the gas, you are increasing those particles' speed. So they are going to hit the walls harder. That impulse, change in momentum, every time they collide will be bigger because their speed is bigger, so their change in velocity will be bigger. This is bigger because the velocity is bigger. Okay. The other thing that happens if they're moving faster is that they hit the walls of the box more frequently because, like we said, they have to get from where they collide across and all the way back to collide with that wall again. And if they're moving faster, that time is going to be shorter. So they collide more frequently. So if we are doing work or heating the gas, again, from a microscopic perspective, the pressure on a given wall increases because the particles are hitting the wall harder, their impulse is bigger, and because they're going faster, and so they're hitting it more frequently.